All right, so we've seen vector subspaces or vector spaces. This is where we have a set, an addition operator, and we're going to there, and a scalar multiplication operator. And you've seen a variety of different things here. We're going to go through a little checklist on these. And what made a vector subspace or vector space a vector space is if we took this combination, so we're given this combo, and then it either did one of two things. It either satisfied all, as it turns out, 8 axioms, then we would say that this is a vector space. And we could then conclude a bunch of other things about that, about the elements of that set, like what the zero vector is, how to build it, how to build the additional inverse. However, it's also possible that if we missed any one or more of the axioms, if they weren't satisfied, then it's not a vector subspace or vector space, sorry. Right. So it's one of the two things. So someone says, here's a set, here's a plus, here's what plus means to me, here's what scalar multiplication means to me. And then you say, oh, okay, hold on. I'm interested in whether this has a particular kind of structure to it. And it either boils down to satisfying all the 8 axioms, in which case, yeah, it's a vector space and a whole bunch of other things can be inferred from that, or it's not quite, it's missing something. And so it's not a vector space. So we can't say much about it at all, given what we're doing. We are very much interested in this side of the ledger. We're going to focus on that. And with that in mind, it makes sense to put you back into the practice of what of the sets that we've seen is a vector subspace. So let me just go back here for 1 second. And there's the code. There we go. So next question. So we're just going to go through a sequence of about 5 of these. What real numbers? Are the real numbers a vector space? Yeah, so for Jaden's comment about the 8 versus 3, I blended a couple of them because they're ones that we don't use very often. Like there's one about the first 2 in the notes, sorry, the first 2 in the lecture. Let me say this one more time. The first 2 axioms that are in the textbook online, I merged into the same one and just said it's, I think it was these guys here. No, I didn't even put them here because we never use them, quite frankly. Though it's not the 0 element, it's not the ones that we use the most. I think it was the commutative and associative. That one I just blended into a single axiom altogether. So if you look at the actual list broken down as finely as we can break it down, it's 8. If you look at my list of 6, it covers all the 8, just some of them have been merged together. So we're not going to ask you to quote axiom numbers, so it didn't really matter. But I appreciate the question. I should have clarified that earlier. All righty, absolutely. So vector space reals, absolutely. How about the integers? And, oops, I want to do that. Okay, interesting. All right. So less confident here than I was hoping for, I'll be honest, but the integers are not a vector space. I'm going to go back to here for a second. And that's because if we take a real times an integer, this is our scalar multiplication, we might not can get a non-integer. For example, if we take pi times 2, in principle, that's fine. That's a real times an integer, but it's the result, pi times 2 is not an element. Pi times 2 is not an element of the integers again. And what that means is this scalar multiplication is not a valid function. From the reals with an integer. We can't combine every real and integer and get an integer back. So that was our whole logic chain when we looked at this one. I think the first day we looked at vector spaces. So one of the things that we sort of got as an intuition was that a vector space somehow is continuous. So you can't have gaps. The reason this is a problem for the integers is because there's a gap between 2, 3, 4, 5, 6. This number here is like 6.5, but that's not a valid integer. So somehow when we do have a vector space, it's got to be somehow continuous. All right, good to highlight that one. Glad we asked. How about R3? Put it in the middle for now. How about R3? So sorry, going back to the integers, I think I just saw a chat thing there. Anytime we define scalar multiplication, it's always the same set. It's always our master set. That is the thing we're multiplying and the thing we get back. And then it's a real vector space because we can multiply by any real number. So there's two sources for the things for the sets that are used in a scalar multiplication. There's the set we're looking at, that comes from here. And then there's the set that we multiply by, the scalars that we're allowed to multiply by. And by default, for pretty much everything we're going to see now, it's all reals. All right. And so what are we doing on R3 here? Fantastic. Yep, R3 definitely is. And how about Rn, the n-dimensional space? So R3 got moved. How about 10-dimensional real numbers, so on? Sorry, ignore this if it's not your question, but also while you're doing that, let's ask about the additive inverse. Actually, the integers are okay for additive inverses because the integers are all the negative numbers as well as the positives. So addition is only ever between elements of the set. We don't have to worry about the reals for that. That's only with multiplication. So we can definitely find an additive inverse for everything in the integers. So there are problems, but we just had to miss one of the axioms to have this all fall apart. It doesn't have to be any more than that. And the integers failed this particular one, but pass a bunch of the other ones. Is there a cheat sheet? I think someone sent it around actually in the chat last time. Honestly, you can just Google the 8 axioms of a vector space and you will get a plethora of this. This is a standard first year linear algebra kind of thing that you'll find everywhere. And WebWork, yeah, WebWork actually had a list in the week 2 thing for that. All right, so Rn absolutely is perfect. All right, Rn is just more space, if you like, higher dimensionality, but it's still something that has that continuity and everything else. And I have one more. Let me do the next one. Oh yeah, this one, yeah. So this, we also defined one towards the end of last week, which was, it was out of R2, but it wasn't all of R2. So we said it's some set that had X and Ys. I should really try to write this correctly here. It's on your screen with the question on the clicker, but just to be super clear here, if I take vectors in R2, so again, all the plane, and then I say, okay, I don't want the whole X and Y plane. I just want X's and Y's that add up to 1. Is that a vector space? If I still use the regular addition and multiplication for vectors, for 2D vectors, there we go. Excellent. Thank you, Nigel. I think you shared that last time. Much appreciated. Oh, interesting. Okay. So this vector space, just so you can see it, we're about 60-40 split on this. All right. Perfect. That's what I'd like to highlight right now. So for reference, what we saw last week was that this set, if we think about all the points that add up to 1, that would be like y equals 1, x equals 0, x equals 1, y equals 0, and all the points then on a line. This, there we go. And this one turned out to be in the not category. So this, we actually called it V1. I didn't want to put that in as a mnemonic, but this V1 set here, and I called it 1 just because we had an equals 1 here at the end, is not a vector space. Okay, now we're going to investigate this further in the next few slides, so I didn't want to go into detail here. But one of the problems we can see right away is the zero vector is not in this thing. So if I'm going to have a zero vector in this set, what could I add to an XY vector and still keep it the same? Well, I'd want to add 0, 0, but I'm not allowed to because it's not in the set. That would be one thing that feels off from this. However, this is opening a broader question for us, which is, do we have to do this work all the time? Do we have to do these 8 axioms every single time? No, we get bored of that pretty quick, especially when, as a number of you pointed out, generally speaking, we don't change plus and scalar multiplication that often. Those are kind of, we have defaults for scalars, we have defaults for two-dimensional vectors, we have a default for functions. We know point by point. We basically recycle those operations a lot. What we change more often are the sets. So out of the 3 things that we talked about a second ago, the set, the addition, and the scalar multiplication, we don't change the addition and scalar multiplication that often, but we might take a big set and then shrink it down and say, well, is this subset still a vector space? And so mathematicians looked at that question and said, well, if we already have a vector space and we're considering a subset of that, so that's exactly our V1 scenario here. We know that R2 with the usual plus and scalar multiplication is a vector space. Right. We've already proven that. We've looked at that. We've seen that. And as long as we keep the same addition and scalar multiplication, the question is, well, is this subset of R2, is that line along here, is that line along there, does that define a vector space as well? Well, this is actually just a subspace of what we started with. And of course, we can do all 8 vector axioms, vector space axioms. We can absolutely do that, but man, it's a lot of work. And a lot of those have to do with the plus and scalar multiplication, and that's going to be just redundant. If we've already done it for R2, it's not going to be any different for the subspace. So it turns out, if we're looking for a known vector space, there's a shortcut. So take a step back. If someone gives you a whole new something plus and scalar multiplication operator, you have to do the 8 axioms. But if someone says, here's a set that we already know, that's in our checklist back here, any of the ones here, we can say, yeah, we know those are vector spaces. And someone says, well, I just want to take a subset, a little piece of this R2, keep the same plus, same scalar, but I just want, there's this little subset of R2 vector subspace. It turns out the job gets easier, and we actually need to work with or show 3 properties. So this is what we have for this. We call this a subspace because we have the V here, which is our big and known vector space. And then we have W, which is the thing we're going to test now. So someone's come along and said, I'm interested in this little subset here. So W is the smaller subset. I think it could be the same one, but usually it's smaller. So W is inside or contained in V. And the key thing is we're not messing with plus and scalar multiplication. Those are the same. So as long as we know that this is a vector space to start with, by changing the set, we're also going to get a vector space, or sometimes called a vector subspace, if it has only just these three axioms. So let's take a look at the list, and you'll see there's sort of a familiar thread to them. We have to have 0 element, just like vector spaces do, but we actually already know that there is a 0 element in V because it is a vector space. So we're just saying, is that 0 element of V also in W? So is the 0 vector from V, so known in advance, we can figure all that out, also in W. We have to have that true. We have to have W closed under addition. And so when we add 2 vectors, they have to stay in W. And we also have to have W closed under scalar multiplication. So if we take any vector in W and multiply it by any real, we have to get something that's also in W. Now we're going to see this play out through a number of examples. So I'm not too worried about this, but you'll see this theme of 0 and closed. And closed means kind of like the integers a second ago were not closed under scalar multiplication. I could take an integer multiplied by a real and get something that's not an integer back. That's not closed. I can get out of the integers by multiplying by a real. What we're asking here is for the set to be closed under addition. So if I add any two things, I stay in the set. If I scalar multiply a real times anything in the set, I stay in the set. So there's kind of this boundedness to that feel to addition and scalar multiplication in a set. And if we have all three of these things, we're done. This thing is also a vector space or a vector subspace. It has all the properties that we've talked about. We basically get to carry all of our intuition and understanding about a vector space into this new set for very little cost for testing these three elements. All right, so let's see this play out with specifically the set we have here. We have our set, we have our VXY. So again, what does this mean geometrically? This is X and Y, and we had the points here. I got the line, there we go. So this is the set V1. And so V1 is a subset of R2. So R2. So it could be a vector subspace of R2. Right? It's perfectly reasonable to take a look at that question. Is it though? Well, it has to satisfy those three properties. Now, I have to be a little careful here. I realize notation-wise, yeah, let me point out the notation-wise issue. I called X and Y here the components of our vector, our R2 vector. And so in the rules down here, I used X, Y in a little different way. So I'm going to scratch them out for the purposes of this page and call them U and V, because I think that's sort of more natural. U plus V. But just be aware, as soon as we said something was an element of W, and W here is my straight line V1 here, all the points in that line. It doesn't matter what we call them, but X and Y is probably a bit problematic because X and Y usually mean our components. So let's call these U and V for the purposes of this page here. All right, so the question one is the zero vector from R2 in V1. I think most of us will say, actually, I wish I had a clicker question for this. Do I have one? I don't think I do. No. All right. That would have been a natural one, though. Is the zero vector in it? Well, the zero vector in R2, and again, we have the subtext of with the usual vector plus and scalar multiplication is, well, it's the 0, 0 vector, right? What do I add to any other vector and not change it? I add the 0, 0 vector. 0, 0 is not in V1 because if I take the component-wise element here, if I take the two elements, 0 plus 0, 0 plus 0, X component, and the Y component equals 0, not equals 1. So right away, we would say that this is not a vector space, a vector subspace, because axiom 1 for a vector subspace, no. For vector subspace is not satisfied, we are done. We can say conclusively that V1 is not test 1, test 2, test 3.
We're back.
Okay. All right. I'm not sure if, I think it's my mic. I think it's showing its age. Thank you for letting me know. All right. Is it possible to be a vector subspace and a vector space, but not a vector subspace? No, is a short answer, because you're always working within this set. So there's no way to kind of finagle around the sides. If you're basically, if it's not a vector subspace, it also won't be a vector space. All right. I'm not sure how much you lost there, but basically it was saying if one of these guys fails, if any one of these three properties is not satisfied, then your thing is not a vector subspace. We're going to see the contrary, where to be a vector subspace, we have to satisfy all three of those and show that they're all satisfied. So let's dive into that. And what we're going to do is tweak this line. Like, this line is not a bad idea, but it has to be a line that includes 0, 0 for some reason. So any subset can be a candidate, sorry, any subset of a vector space can be a candidate subspace. And then we just say, is that subset yes or no? Does it follow all the rules of a subspace, of a vector space? And so one tweak to this set is that we have x plus y equals 0. And that's the same if we rewrite it out as a more natural line formula. It's the line y equals negative x, which is the straight line going down and going through the origin. And so we would ask the question, one, is the 0 vector from R2 in this V0? And yes. 0, 0 is the 0 vector in R2, is the 0 element in R2. And if we take the x component and the y component of these, 0 plus 0 equals 0. So 0, 0 is an element of V1. This is the condition, the V1 membership condition. What makes something in V1 or not in V1, then we have that. Sorry, V0, thank you, V0. All caught up in that, V0 membership condition. Thank you. So that was straightforward. All right, the next two are a little hairier. So if we take any point on this line and we add it, so closed under addition, do we get another point on the line? That's what this closed under addition means. So I'm just going to sketch that out again. Take this line and 5, there we go. All right, if we take this line and we take any 2 points, and again, I'm going to change my notation down here. I'm going to call it U plus V, sorry, U and V. Take any 2 elements on the set, and if I add them together, I get another element of the set. So this is a vector U and a vector V. Is that also in the set? All right. Well, let's let U be one element. And you have to keep this very general because we have to show that this works for any 2 elements anybody could possibly pick. We're going to pick that to be, let's call it x1 and y1, and v equal to x2 and y2. Now, why do we need to kind of give these components? Well, because the definition of membership is defined based on the components. And because, let's keep going here, because U is an element of V0, that means that x1 plus y1 is 0. And because V is in V0, V0, x2 plus y2 has to equal 0. Again, this is just from the membership condition or requirements for V0. Right? You're only in V0 if you actually have that sum of your 2 components adding up to 0, or you're on this line, same condition. All right. Then we take a look at U plus V. And we're trying to say, is that addition also in our set? Just one, I think we're back. All right. If we add these 2 things, that's the same as adding x1, y1 plus x2, y2. And that's going to be component by component elements. This is just regular R2 addition. X1 plus x2, that's getting too fancy. And y1 plus y2, there we go. All right. look at, is U plus V in V0? Yes, because if we take this component, that's x1 plus x2, that's the x component. Oh, that was weird. That was unexpected. What was it? X component, and we add it to the y component. Why do we do that? Well, because that's how we decide if something is in the set or not. So we add y1 plus y2. That is equal to, I'm just going to regroup it a little bit, x1 plus y1 plus x2 plus y2. And that is equal to 0 plus 0. And why is this? This is because U and V are in the set already. And that, of course, equals 0. So if we take our U plus V and we add up their components, we get 0. Well, that's exactly what it means to be a member of this set. Careful. So the question there from Daniel. When we're doing addition, it's always 2 elements of the set. When we're doing scalar multiplication, we'll see that in a second. That's 1 member of the set and 1 real. So it's a different scenario for addition. Addition is 2 members of the sets always. And scalar multiplication is 1 element of the set and 1 real. So it's just different rules. All right. Let me just pause there for anyone still copying those notes, and then we will do this. Why does this equal 0? Because we said U is in the set. Sorry, I should have actually said that. Oh, there it is. U is in V0. That means that its components add to 0. That's what it means to be in V0. Oh, so this is writing out, what does that mean? My 2 components are this and they add to 0. All right, let's do the third one. Not for completeness here, we have to do all 3. So this is something that we do ask students to do quite regularly is, here's a vector space you know and love. I'm going to define the subset on it, decide whether it is a vector subspace or not, and prove that. And that means either show that one axiom is not met, one of the 3, or prove that all 3 are satisfied. So this is a very typical kind of test question and assignment question. All right, last but not least. So 3, we're going to let U be an element of our set, V0. And let's do it the same thing. We said U is equal to, this time I'm just going to say XY, I think. We don't need a 1 or 2. And I think we used alpha down here. So let's let alpha be a real number. So again, we are going to check whether if I take any vector and multiply it by any real number, I still get an element in the set. And so again, what we have here, because this element's in the set, we have x plus y equals 0. And then we're going to look at alpha times u. Well, that's alpha times xy, and that is equal to a vector that's alpha x times alpha y. And why? Because here we're actually using a regular R2 vector scalar, sorry, not vector scalar, scalar multiplication of a vector, scalar product, scalar multiplication of a vector. And alpha times u is an element of V0 because we're going to take this, that's our x component, alpha x, and we're going to add that to our y component. Why do we want to add those? Why do we want to compare them at all? Because that's how we test whether you're in the set or not. So if I'm going to be in the set, I need to know whether this x component plus this y component adds up to 0. Well, that's equal to alpha times x plus y. And that's equal to alpha times, oh wait, we already said this, x plus y has to equal 0 times 0, and that's equal to 0. This is because u equals xy was already in V0. All right. Okay. So our alpha u is also in V naught. And so if we want to be thorough here, we'd say this set V naught is closed under scalar multiplication. And so that, going back one step here, going back 2 steps actually, we were asked the question, is this subset here? So R2 is a vector space. We all know that. We've been using it for years. If we define this subset here, does it follow all the rules we need to have it follow to be a vector subspace? And the answer is yes, because we actually went through explicitly all 3 steps, all 3 requirements. Is the 0 vector from R2 in there? It absolutely is. We can check it, make sure it satisfies this condition. If we take 2 vectors that do satisfy the condition and we add them, do we also get a vector that satisfies that condition? Or if we take 2 vectors on this line and we add them, do we still end up in a line? We absolutely do. Good, that's the second condition. And then again, if you think about scalar multiplication in R2, what does that do? What does scalar multiplication do? It stretches vectors. So if you had a vector that was this far and then we scaled it, or multiplied by negative numbers, we're still going to stay on that line. So that's another way to think about the closedness under scalar multiplication. If I take one of these vectors and then I scale it, or I flip it and scale it, do I stay in the set? The answer is absolutely yes. So we're good there. And so I think I need one more page here. Page, insert page. The conclusion is because V naught satisfies, 3 things. V naught is a subset of R2, a known vector space. I think audio went off again there. It satisfies all 3 subspace axioms. That means V naught is a vector subspace, or if you want, we can also just say vector space. Sometimes it doesn't really matter which one we say. We think of subspace just because it is a subset of R2. It kind of belongs to that, but it is a vector space with all the rights and privileges of any vector space, however it was defined. So, sorry, quick time check. Okay, good. So the questions that came up in the chat, is it possible to have examples that pass axiom 1 but not axiom 2? Absolutely. I think you'll actually see that in one of your web work questions and or tutorial problems. So the reason we have all 3 properties is because it's possible to fail on any one of them. I think it's hard to get something that fails on 1 but not 2 and 3. Like there's different levels of challenge for the creativity, but it is certainly possible to have something that satisfies the first 2 but then fails number 3. So yeah, I always go in this order. It's just it keeps it consistent, and it's only 3 things, and usually you can check pretty quickly each one. So yeah, I just go in that order every time, just to mostly keep the mnemonic of 0, addition, scalar multiplication. That's kind of the order we think of them in anyway. So stick with that order for checking as well. All right, I'm going to throw it back to you. We're going to do 2 quick clicker questions. Think about those 3 axioms. So 0 element, closed under addition, closed under scalar multiplication, and think about how or if the set of just the 0 vector. So imagine this could be in R2. So if we take R2 as our main space, as our big space, and we just limit it down to the origin. Just go down to the origin, 0, 0. Is that a vector subspace? That question up on clicker. There we go. Again, using the rules, regular rules for R2 for addition and scalar multiplication. I'll follow through question afterwards. I think, Rohan, I'm not quite sure it's a well-defined question. So, all right. We're doing there. Interesting. Okay, that's 75, 25. All right, let's dive into the All right, sorry, I think I'm still having more audio issues. All right, so 1, is the 0 vector in W? I think we can all agree yes, because it's the only single vector in there. It's the only thing that's in there. So yes. 2, closed under addition. Well, that means take any elements, take the sum of any 2 elements of W, and ask, is the sum in W? Sum also in W. W. Well, the answer to that is yes, because the only thing you have to add is 0. So if I take 0 and I add it to the 0 vector again, well, one of the properties of a vector subspace is that we get the 0, and that is also in W. There's nothing else we can add because 0 is the only thing in our set. And 3 actually is pretty easy. Alpha times the 0 vector is also the 0 vector. We showed that as one of the extrapolated properties of vector spaces. So W is also closed under scalar multiplication. Closed under scalar multiplication. No matter what real number you pick, if you multiply the 0 vector, think about this in just regular space. If you have someone hand you the 0 vector and says, here's 5 times that, then you're still at 0, 0. So we have that property there. And so, yes, the 0 vector by itself is a vector subspace. The set of 0 in some world where we have a vector space already, if I just take the 0 element out, we do get a vector subspace. All right. Additive inverse. The only thing we have to inverse, well, actually it's right here. What element of the set, let's pick 0, what can I add to it and have it cancel and get the 0 vector back? No, it's its own additive inverse. So 0 is its own additive inverse because if I add it to itself, I get the 0 vector back, which is the condition for additive inverses. Sorry, so the question is, we're working so far with sort of the reasonable, the natural, the familiar, that's probably the best word, the usual or familiar vector addition and multiplication, scalar multiplications. As long as this, whatever it is a vector space, the 3 axiom tests, everything else that we're doing here for testing for a subset of it would still apply. We're going to stick with these for most of our examples. I think you might see some in tutorials where we get a little deeper in, but the key thing is that this triple, your big vector, your big set, your addition and scalar multiplication operators all together, that they're a known vector space, and we're just looking at some piece of V, some subset of V here, lines or dots out of that big space. As long as it passes those 3 tests, these 3 conditions, then you have a vector subspace. All the rules for vector spaces apply to that subset as well. Alrighty, so yeah. Let's actually try the next thing just quickly because I have a clicker question ready for this. What about the empty set? So if I take the empty set, which I think I drew not quite the right way in the version there on clicker, sort of the phi here. And I'll talk about the 0 vector thing in a second once we have that question wrapped up. Perfect. Okay. Yes and no. Fantastic. So a bunch of no's there, and that is perfect. No, because the 1 requires that the 0 vector be an element of the set. So let's call this a W. W, but W is empty. So 0 is not an element of W. And that means right away that W, which is the empty set, is not a vector subspace. So it's an interesting distinction. Programming people would have this same experience of a null set is different from a zero value. There's some common ground there that zero is kind of nothing, but it's not nothing in the same way. So just be aware of that. I can have a single element 0, and that satisfies all the criteria for a vector subspace. But as soon as I say there's no elements at all, nothing in that set, then no, we don't have a vector subspace. All right. It's not the curly brackets are magic. The empty set is handy for intersections. Like it just describes a different scenario. So yeah, we're going to tell you, sometimes we care about the distinction between there is nothing in my set. I have no objects versus I have the number 0, and that has properties, and I can add it to itself. I can do something with the number 0 that I can't do with an empty set. So it's a subtle distinction, but sometimes it's relevant. Yeah. All right. So let me just do a quick thing on this. I'm not sure I'm going to be able to address the question because I feel like it's sort of a vague uncertainty thing. But the 0 vector in some set, in like say in R2, is equal to the vector 0, 0. That is a different thing than the 0 value, the single real number, different from 0 element of the reals, a single real number. So that's a distinction. And also the 0 vector is 0, 0 under our usual, so it's different from that, our usual plus and scalar multiplications. One of the examples I think you've all had in web work was the 0 vector in R2 with different plus and scalar multiplications may not be 0, 0. Right? If you change what plus means, then it's not, remember the property that defines 0. This is defined by any vector u plus the 0 vector gets you back to the same u vector. Well, if you go and mess around with what plus means, then you might not have the same, you might put something else in here for the 0 vector, not necessarily 0, 0. You might put something else. In fact, this is in your web work as an example. So if someone goes and messes with the plus and scalar multiplication rules, guess what? That has effects throughout the space. You may have to change your mind about what that means. We will let you know. Again, it will be brutally obvious. We will say, by the way, no, we insist that our plus now means this. Our scalar multiplication now means this new rule. We will highlight that. Otherwise, we're going to keep with the regular rules. We don't say anything. But if we want you to mess around with this plus and scalar multiplication operator, we will announce that as almost the first thing in the question. And one of the consequences you have to be ready for is, yeah, you got to broaden your mind a bit. 0, 0 may not be the element there. Now, I won't go into the weird. If you take a look back at the weird vector space from the end of last week, it wasn't all of R2, but it was this upper part of R2. And there we had the 0 vector. The 0 vector in that was actually equal to 1, 1. So again, the 0, 0 vector, the element 0, 0 is the thing that satisfies this rule for your addition operator. That is what it means. To be the 0 thing doesn't tell you anything about what's in it. This 0 thing is the rule or the element that satisfies this rule. So I'll get you to wrestle with that going forward. All right, a couple more examples. So we have C infinity. This is a set of functions, right? This is our continuous and infinitely differentiable functions. Okay. Inside that there's a bunch of sets, but one possible set we could define is the set P5, which is all polynomials of degree 5 or less. So, for example, x to the 5 minus 3x plus 2 is a hypothetical member of this P5 group, P5 set, e.g. So that would be a polynomial degree 5. Sine of x would not be in P5. Sine of x is not in P5. They're both, though, continuous and infinitely differentiable functions. So they're both in C infinity, sine and this polynomial, but only the x to the 5, that thing there, is in P5. Alrighty, is that a vector subspace? Well, yes. Again, just from an intuition, the first thing, is the 0 element of our big set in the polynomial set here? Yes. The 0 vector here for C infinity is the 0 valued function. Sorry, why is sine x not in P5? Sine x is not a polynomial. P5 is polynomials of degree 5 or less, so it has to have this kind of form. Sine x isn't that. So the 0 vector for C infinity is the 0 valued function f of x equals 0 for all x. So again, this is why calculus gets sloppy about things, and it kind of comes to bite us in the butt here. There's a 0 vector, it's a 0 element in a set. So maybe not 0 vector, maybe 0 elements, again, a better way to phrase it. It's something that if I add to any other function, nothing happens. I don't change the function. But it's not the 0 number, it's actually a graph. This is, if I graph an x against f of x, there's a 0 element, which is the 0 function across all x values. And it is infinitely differentiable, it's continuous, it's all that nice stuff, but it's not the 0 number, it's a function. So as long as you're aware of that, the 0 function is in there, and that 0 vector, which is the all 0 function, all 0 valued function, is in P5. If you want, you could call it 0x to the 5 plus 0x to the 4 plus 0x cubed plus 0x squared plus 0x plus 0. That is a perfectly valid element of P5, and it's also equal point by point to the all 0 function. And so you would be good to go there. So yeah, we've got the first condition met. Check. Oh, crap. All right, I'm going to quickly rush through arguments 2 and 3, and then it'll be optional for people who have time and can stick around if they have questions. So I'll catch up on the chat too. Is it closed under addition? P5 is closed under addition. And what does that mean? Add any 2 polynomials of degree 5 or less, and the sum is also a polynomial of degree 5 or less. And you can see that by a quick addition. Let's call it, let f1 be a5x to the 5 plus a4x to the 4 plus all the way down to a1x plus a naught. And sorry, just f. And g be b5 x to the 5, b4 x to the 4, b1x plus b naught. All right. This is a generic polynomial. I allowed any coefficient I wanted, but I have the maximum degree of 5. And it could be degree less if I just had 0 values at the front there. So I should put a little subtext here that the a naught 1 so on are all reals. And likewise here, all the b naughts, b1s and such are also reals. So this describes, you pick any 5th degree polynomial, I can describe it with this. Pick any 5th degree polynomial, I can describe it with this. And finally, if I look at f plus g, it is going to be a5, b5, x to the 5, plus a4, plus b4, x to the 4, all the way down to a naught plus b naught. And that is also a polynomial of degree 5. It's still x to the power 5 with some constants out front. So that is also an element of P5. Let me just pause there for 1 second before I go on to the third slide, but you can kind of see where this is going. The third condition is that I should be able to multiply by a scalar, not by anything else, not by x's, but by any real number. I should be able to multiply this thing here. In fact, I'm going to steal it. I'm going to multiply that by a scalar, and I'm going to get another polynomial. So condition 3, P5 is closed under scalar multiplication. Shouldn't try to rush scalar multiplication. But f this, which is an element of P5, it's a 5th degree or less polynomial. And let's let alpha be a real. Alpha times f is going to be alpha a5, x to 5. Because how do we do multiplication by a scalar? We just multiply it into each term 1 by 1, and it multiplies the coefficients. Alpha a4, x to the 4, all the way down to alpha a0. And that is, sorry, that should be an element. That is also an element of P5 too. And that means because all three things are satisfied, P5 is a vector subspace of C infinity. Ooh. All right, I apologize for the rush on that examination there. What I would say is, sorry. Oh, sorry. Oh, that's moving to a new slide here. Sorry, got ahead of myself. Yeah, we'll do that. I'll make space for that on the next class. So yeah, we're going to look at some other definitions of other subspaces of C infinity and see if it's true that all subspaces are or aren't subspaces. All subsets are subspaces, and we'll explore that next class. All right. So we'll pause there. We'll stop there for the lecture material, and I'll take a look at questions in the chat from now on. If you have other places to go, please by all means do that, and I will follow up the chat.